So today we're going to talk about inverse trig functions. You guys know what inverse trig functions are, at least you've used them. Back in geometry when the trig functions were first introduced to you as SOHCAHTOA problems, and some of those problems required you to solve for missing angles inside of triangles. You had to use inverse trig functions to solve those equations. But there's a little bit more, something a little bit more intricate regarding inverse trig functions, regarding how they're defined, how we limit the range of these functions, and that's kind of what we are going to be getting into today. So a little bit more advanced concepts. Now, you may be asking, what do volcanoes have to do with any kind of trig functions? And right now, you're just going to have to hold that curiosity and temper it until we can examine exactly what's going on with the volcano. Two questions before we really get into the heart of our conversation today. The first question is a question of inverses. What are inverses in general? Well, as far back as probably pre-algebra, you started discussing the concept of inverse operations. Addition and subtraction undo each other. Those are inverse operations. Division and multiplication, squaring and square rooting. These are all inverse operations. And then we, in Algebra 2, started talking about functions that actually undid each other. So that's what this little diagram shows. We have a function f, right? There's our function f, and f is going to take an element of the domain. In this case, it's going to take element A, and it's going to operate on that in some way, and it's going to turn it into a new element of the range. And there it is. There's B. A has turned into B. Or you can think of it as x turns into y, however you want to consider it. But f of A is equal to B. Another way of thinking about this is if we graphed this function f, we know that the point A, B would be a point on our function. So where does the inverse come into this? Well, the inverse wants to undo what the function did. The notation that we're using here in this case for inverse function looks like f to the negative 1, but it's not an exponent. It's not 1 over f. This is f inverse is how that's read. And what it wants to do is it wants to reverse the process of the function f. It wants to take all of the elements from f's range. And so you can see that the range for f was a red set, right? And that same set, that same red set, is now the domain for f inverse, that same set of numbers. We're calling it the domain now. It's the same little red set, but we're now putting those numbers into the inverse function, and so it's called the domain, but it's the same exact numbers. And what we're going to do is we're going to put those values into the inverse function, and if the inverse function does its job correctly, we're going to get back the original element that we started with. It's going to turn the b back into a, and so f of inverse of b is equal to a, or this function will possess the point BA. And it's an interesting this is an interesting kind of point relationship here. This is a type of reflective symmetry when you look at it graphically through the origin, the line y equals x. Something that you will definitely examine in more detail in math analysis, something I'm sure you're looking forward to. But this is, in general, what the inverse function will do to a function. Okay. Now, more specifically, what does this mean for us in trigonometry? Well, what does a trig function do in the first place? This is something you probably discussed briefly back in geometry, something you probably discussed briefly earlier in the semester here. But let's discuss it a little bit more than briefly here. Let's make sure we really understand what's going on. We learned that the trig functions relate an angle, for example, theta, to a ratio. Now, because I have the sine here, and we could have used technically any of the 6 trig functions, but we use sine. And so specifically the ratio that we're dealing with, right, will involve the opposite leg from angle theta and the hypotenuse. That's our ratio right there, opposite over hypotenuse. Now, what this means is that we're going to take this angle, theta, and we're going to put it into the sine. It goes in right here. So what we put into a trig function is an angle. What comes out of the trig function then is some ratio. In this case, the specific ratio, is the opposite over the hypotenuse. That's what a trig function does. The trig function tells us the ratio between 2 sides of a right triangle based on a particular acute angle within that right triangle. It's the way it's always been. It's a fairly simple concept, and so you don't usually think about it. You just use these trig functions to solve problems. You don't really think about what they're doing. But because we're talking about the inverse trig functions, I think it's worth this closer look, this closer examination. So think about reversing that process then. What would an inverse trig function be doing? Well, it would be taking the elements from sine's range, which are all those ratios, and plugging them into the function, into the inverses, so the ratio becomes the domain, and it turns them back into angles. It turns them back into the angles that generated those ratios. That's the process here. So the sine of an angle is a ratio. The inverse sine of a ratio is an angle. And this is not unique to sine. This happens for cosine. This happens for tangent. This happens for all of the reciprocal functions. You put angles into your standard trig functions to figure out what the ratios are based on whatever 2 sides we're talking about. For secant here, right? That would be the hypotenuse over the adjacent. And the inverse function takes a ratio and tells us what angle would produce that ratio. Inverse trig functions can be read a couple different ways. Y is equal to the inverse sine of x could be read as y is the angle whose sine is x. Y is the angle whose sine is x, meaning y would, if it was put into the sine function, generate the ratio of x, which is more of what the blue explanation gets to a little bit. Y is the angle which produces the sine ratio of x. Now, that's a little bit redundant because a sine is a ratio. If somebody came up to you on the street and said, all right, for $1 million, what is the sine of theta? You would say, well, that's a ratio, because that sine is going to take that angle and create a ratio out of it. So that's what we're getting at here. Put angles in the sines and they give you ratios. And then the inverse functions are going to take those ratios and produce the angles which had generated them. Here's a little activity to make sure we understand this overall concept, okay? You can actually find it on page 11 of your workbook if you're playing along at home. Keeping in mind that the sine of an angle is a ratio and the inverse sine of a ratio is an angle, let's look at some sample expressions. What the heck is it? Sounds like a good game. Our very first example here, example 1, is taking a sine function of an angle. Now, what's more important to look at here? What some people are going to do is they're going to focus on what's inside the function. You're going to say, well, look, 71 degrees is clearly an angle. And so because that's an angle, the thing that must come out is a ratio. And they would be right. They would be right. Sine of 71 degrees is absolutely a ratio. However, some angles look more like ratios than they do like angles, and some vice versa. Some ratios actually can look very much like angles. And so you can get confused if you just focus on what's inside the function. It's much, much safer. Just focus on what kind of function it is we're dealing with. If you just focus on that part of it, you'll be much better off. Sine is a standard function. And a standard function generates ratios from angles. You put angles in, ratios come out. And so the answer has to be a ratio. So instead of worrying about the 7/8, which on number 2, which certainly appears to be a ratio and is, just worry about the fact that it's an inverse function. An inverse function takes a ratio and turns it in to an angle. And so just based on that, we know that the inverse sine of 7/8 is an angle. Number 3 is one that looks a little more confusing just because pi over 12 looks kind of like it should be a ratio. But we can't put ratios into standard trig functions. That's not allowed. You're only allowed to put angles into standard trig functions. So, pi over 12 is just a radian angle measurement, and the cotangent of an angle is going to generate a ratio. The problems starting around number 7 get a little bit more interesting, or as you might like to say, a little bit uglier, because they're composite. It's a function within a function. And if you just focus on what's on the outside, you can still pretty much get the answer. That's a standard trig function, right? And standard trig functions take angles and produce ratios. But if you break it down, it does make sense, because negative 2/3 is a ratio. And this inverse trig function is going to take this ratio and turn this whole thing into an angle. And then the sine of an angle does give us the ratio. So the advice I would give you on these composite functions like 7, 8, 9, and 10, these composite expressions, is make sure you start from the inside, work your way out, but always look at that furthest outside function really to tell you what you're dealing with, okay? Looks like we got 6 left, and this might be a good time to pause the video and try a couple of them out. If you do that when you come back, I'll give you the rest of the answers, because that's just the kind of guy that I am. Pause. I imagine you're excited to see just how accurate your answers were. So let's get right to it here. Number 4, the cosine of a negative theta. I would focus more on the fact that cosine is a standard trig function, and standard trig functions are only allowed to take angles and turn them into ratios, whereas inverse trig functions, like inverse cosecant here, are only allowed to take ratios and turn them into angles. Now, this looks a little more confusing though, because seriously, I mean, 321 doesn't look like a ratio. It looks like 321 degrees, except there clearly is not a degree sign on that value. It could be 321 radians, I suppose, except it can't be. It can't be an angle, because cosecant inverse cosecant, is an inverse trig function, and the only thing you're allowed to put into an inverse trig function of any kind is a ratio. And so if you would have said right from the get-go that the answer must be an angle, you would have been right. Same thing with number 6 here. This is an inverse trig function, and that means that it will turn a ratio, which 7.21 is in a ratio, 7 and 21/100ths. It will turn that ratio into an angle. What about the composite ones? Well, we already did number 7, and we figured out that number 7 was going to be a ratio. Number 8, well, cotangent of an angle, right? Cotangent of an angle is going to, this whole thing is going to become a ratio, and the inverse sine of a ratio is going to be an angle. And you could have gotten that right off the bat, like we mentioned, by just noticing we had an inverse function out here. But it certainly is good exercise to start from the inside and work your way out. For example, this next one, 15 pi over 7 is a radian angle. The sine is going to take that angle and turn the whole thing into a ratio. The inverse secant function is going to take that ratio and generate an angle. And finally, the cosine is going to take an angle and turn it into a ratio. And sure enough, the inverse cosecant of the ratio -8/1 is just an angle. This whole thing inside is an angle. Cosine of an angle is a ratio. So hopefully that helps you understand that process a little bit. If you can keep that clear, it will save you from a lot of, what do you want to call them, unforced errors, mistakes that you just don't want to make. At least it allows you to look at a problem and say, what should my final answer be? Because it certainly is not uncommon for students on a problem like this to give an answer that is the opposite of the type of value they're supposed to be giving. For example, the answer is supposed to be an angle, and their answer is a ratio, which means they clearly just didn't understand what the expression was asking for at all. All right, I said there were two questions. We answered, or at least discussed, the question of inverses. I hope we understand a little bit more about what those are doing. The next one is a question of functions. A question of functions? What the heck does that mean? This is really a little bit more to the heart of what we need, the decisions we need to make here coming up. What's the answer to this expression, the inverse sine of 1/2? A lot of students who have been in trig for a semester or at least a couple months will say, well, heck, that 1/2 is right out of one of the special right triangles. It's the short leg in the unit circle at a 30-degree angle, and they'll say, the answer is 30 degrees. Or if they dig the radians, pi over 6. And that is absolutely correct. The problem is not every student is going to be quite so simplistic. Some students might say, well, I would choose 150 degrees, which, if you think about it, in quadrant 2, right, is a 30-degree reference angle, and because sine is still a positive ratio in quadrant 2, y is still positive, the answer is, again, going to be 1/2. And then we get into the whole concept of coterminal angles. Like, well, what if I went all the way around another 360 degrees here? So 150 plus 360 would be 510 degrees. Well, guess what? You're going to get another ratio of 1/2. And it doesn't take long before we realize that there are an infinite number of correct angle answers to this very simple expression, because the trig functions generate values going around and around a circle, meaning they continue to hit the same ratios again and again and again in either direction. You could go backwards. Another way to get to 30 degrees would be to go in a clockwise direction for an angle of -330 degrees. That's another answer to this function. And so we have a problem with that. Why? Well, once again, what are functions? What are functions? What must be true for any function to be a function? Here's the deal. If an x value goes into the function and goes to a particular y value, then for a relationship, for an algebraic or trigonometric relationship to be a function, then if we ever go back and we put that same value back into the function, it has to always give us the same answer. That's a function. If for some reason we went back into the function and the same x generated a different y value, this relation just lost its function status. That's illegal for functions. This is a discussion you guys had in Algebra 2, and you learned some tests to see if things were functions or not. But this is the main premise right here. It is okay for different x values to go to the same y value, but you can't have the same x value go to different y values and still have a function. And this is exactly what just happened. Our inverse sine function just failed this this little test. 1/2 went into the inverse sine, and the very first student said, well, it's 30 degrees. But then remember, that next student was like, no, it's 150 degrees. And then people started catching on, like, hey, I'm going to be smarter than the guy before me. And suddenly everybody in the class wants to give another answer. And finally the last student, who has the calculator all fired up and wants to be the funniest of all, is like, oh, 14,430 degrees. But by that point, everybody's like, it's not funny anymore, dude, so put your calculator away. I think you get my point. The inverse sine function is majorly failing. You could try this on your calculator. You could start, make sure you're in degree mode, but start plugging these angle measurements into sine, I mean. Just do sine 30, sine 150, sine negative 210, sine negative 330. Every single time, your answer will be 1/2, 1/2, 1/2, 1/2. And so here's our question today. Here's what we're going to try to decide. How can we create a function relationship for inverse sine when clearly at the present there isn't one? Here's a graphical look at the issue. This sine graph is one we haven't seen, I guess, in, I don't know, a couple weeks, but we certainly are familiar with it from days past. And if we took this sine graph, the entire, at least the 2-period sine graph you see right here from negative 2 pi to 2 pi, we reverse the domain and the range. Now consider what this means. This means that the domain, which was all these angles in here, right? All these angles, now becomes the range. So now the y-axis is all the ratio angles, or I said ratios, I meant angles, like negative pi and negative 3 pi over 2, pi over 2, and so on and so on. Meanwhile, the original ratios, remember, the only ratios we could ever get from sine were from -1 to 1, because a opposite over hypotenuse ratio can never be bigger than 1. Well, those now become our domain. And so the ratios go into the inverse sine, and the angles are going to be coming out, right? So if we just graph this, just as we've been discussing, here is a picture of what we would come up with, okay? Slight modification to make sure it fits here, and voila. That's pretty much what we'd have right there. If you remember one of the simplest tests from Algebra 2 that you were taught, called the vertical line test, you will immediately see why this function is an issue. Here's my vertical line. And you see how I'm hitting the graph multiple times? In fact, if we kept going, snaking up and down the y-axis, this vertical line, or any other vertical line between -1 and 1, would hit the graph infinitely many times. So it's not just a slight case of failing to be a function. It's a drastic case. In Algebra 2, you may have been looking at y equals x squared and said, oh, well, what if we solved for x? If we solve for x by taking the square root of both sides, we'd get plus or minus the square root of y is equal to x. And then if we said that this is our new function and graphed it as f of x is equal to plus or minus the square root, and then we turn the y back into an x since it's a domain element now, we would graph this dude, and we would end up with something that looked like this. And this is probably one of the first times when your teacher said, hey, this is a problem. The same x value is going to 2 different y values. This doesn't pass the vertical line test. Well, that's a simple case of not passing. The inverse sine is a tremendously more complex case where you have infinitely many failings. What are we going to do? how are we going to handle this inverse function? You know, back in Unit 3, you had problems like this, where we had to solve for theta. And so what we did is we solved our way all the way down until we had the trig function of the angle. And then we went and we went to the table and you know, figured out because it's negative, it would be in these two quadrants, and the answers would be this and this. But here's something that was always part of the problem. The values were always within an interval. And that certainly is one way that you could limit how many answers. Otherwise, you know, you could have generated infinitely many answers for this because of the coterminal angles. But even from 0 to 360 would produce multiple results. In fact, for this case, you'd be 2 pi over 3 reference angles, or 60-degree reference angles from quadrants 2 and 3. And you know, you can't even have 2 answers to have a function. That's not going to work. But we are going to limit it, and we're going to limit it in a much more logical way than just kind of saying, let's just go from 0 to 2 pi. This is a geometry problem all the way back from your geometry class, where you just were solving for an angle. And what we did here is we set up the relationship. We had the opposite in the hypotenuse, and so we said the sine of theta is opposite over hypotenuse, 1 over 2. And then, as you can see right here, we took the inverse sine of each side so that we undid the sine, and theta was equal to the inverse sine of 1/2. And then we plugged it into our calculator. I think everybody remembers doing a problem like this at some point, right? And our calculator gave us an answer. I wonder what that answer was. How about 30? And this was in degree mode, so our answer would be 30 degrees. And then we move on to the next problem. But notice that you could have, you know, 50,000 students. If they were all in degree mode, they would all get the same answer, 30 degrees. So even though not everybody in a classroom might agree on the answer to this question, the calculators always agree. Why is this? Well, because hundreds of years ago, mathematicians agreed about the same results we're going to come up with today, and calculators, since they've been in existence, have always been programmed with these agreed upon ranges for inverse trig functions. And so that's what's going on. Our calculators only give us one answer when using the inverse trig functions. How is it deciding to do this? Well, it's just how it's been programmed. And we're going to discuss why it's programmed that way right now. This is what we've been building up towards, is the discussion of the inverse trig functions and the lava zones. Here's the deal. The sine is going to take all these different angles and turn them into ratios between -1 and +1. Now, if I'm going to try to get an inverse function, if I'm going to be able to generate or at least accept all of the original ratios that the sine function was generating, I need to have all the positives and all the negatives. So if you just think about going from, say, 0 to pi over 2, what this is going to do for us is generate all of the ratios from 0 to 1. We just got ourselves half of the answers that we need. Around the unit circle, what we did is we traversed, remember, sine in the unit circle is just the y value. And so as the y values go up, they get bigger and bigger, starting at 0 until we get up to 1. However, we haven't hit any negative answers yet. So what are we going to do for negative answers? Well, if I continued into quadrant 2 here, if I continued into quadrant 2 here, that doesn't do me any good. I've already hit all of these positive ratios once in the first quarter rotation. All I'm doing now is hitting them again, moving in a reverse order. That would violate the function deal already. We'd already have a failing function because of that. So that doesn't help us. So we need another idea. So let's say no dice for quadrant 2. Now what if we went into, say, quadrant 3? So what if we started at pi and then headed towards 3 pi over 2? And so the idea here would be to take these quadrant 3 values. Does that help us? It absolutely does. It helps us quite a bit. It gives us all the negative ratios from 0 to -1. This would allow us to be able to put any possible sine ratio into the inverse sine function and get an answer. However, there is something that's not very desirable about defining the range of inverse sine as going from 0 to pi over 2, and then from pi to 3 pi over 2. And you can see it with the interval, you can see it with the graph, you could see it with the unit circle. They all display the same undesirable result. And that result is open space. Okay, we've got all this open space here. We've got, the discontinuous region here. Even with our interval up here, we've got that range right there. This is not what we want. We don't want a broken up region. And so we actually say no dice. Now, if we had continued on and said, what about, going into unit 4? Well, we'd still get negative ratios, right? We'd still get negative ratios over here, but it's even more disconnected, or is it? And this is the kind of the tricky part about a circle, but it's also the nice part about a circle, is that circle is just going to keep going around and around. And this region in quadrant 4 is not connected if we're talking about it by discussing 3 pi to 2 pi, 3 pi over 2 to 2 pi. But it is continuous if we went back a full rotation and discussed it from negative pi over 2 to pi over 2. Now we have a continuous region of the unit circle, or of the trig graph, which generates both all negative ratios and positive ratios. And so this is the solution to our first question. How are we going to define the range of the inverse sine function so that we're only allowed to get one angle per ratio, but we cover all possible ratios? That means we could put any ratio from -1 to +1 in. And you can see that we have room from -1 to +1 for any of those ratios to go into a inverse trig function. And we have a continuous span. And so that's how we do it. We use quadrant 4 and quadrant 1, but it's connected from negative pi over 2 to pi over 2. And that's what this discussion is about right here. We're just summarizing it. We can't use quadrant 2 because we've already gotten all our positive ratios from quadrant 1. I could get negative ratios from quadrant 3, but we don't like that because it's not continuous. And I don't want to go all the way around and be discontinuous into quadrant 4 for those negative ratios. But you know what I can do is I can just drop straight down for those negative ratios. And so that creates this span right here for the inverse trig span. Negative pi over 2 to pi over 2. Same exact this thing we just talked about. Now, remember those volcanoes, or at least the volcano at the very beginning of our little discussion here? Well, finally we get to see where it comes into play. If we have a sine ratio that's positive, it's always going to be a very, very simple answer to get because we know it's going to come from quadrant 1. Quadrant 1 is where every inverse trig function, and not to give away the rest of our discussion here, but every trig function has positive ratios in quadrant 1. And so all of our inverse trig functions are going to have their they're angles for positive trig ratios coming from quadrant 1. The big question is, what if those ratios are negative? Well, we just discussed the inverse sine is going to have those negative ratios coming out of quadrant 4 down here. I can't get them from quadrant 3, because if we go into quadrant 3, we go into not just zones, quadrants that are outside of the agreed upon range for our function, but indeed lava. They're lava fields. And so this reinforces the concept that it's not a very good idea to head that way. In fact, it could have very unhealthy results. Turns out that trying to wade through lava fields is not very healthy in any way whatsoever. In fact, watch this little dude. Let's say this little dude wanted to try to make it down to quadrant 3 for a negative ratio. And there he goes. He's gone now. Who knows where he's ever going to pop up again. He's probably right under this spout of lava right now. Oh, there he is. He's probably not having much fun. Are we ever going to see him again? Wait. There he is. And he doesn't look too good. Looks like he's got a little bit of a fire problem, being that he's on fire, which I would consider a problem. You can't go into quadrant 2 or 3. Not only can you not stop in quadrant 2 or 3, you can't even pass through those quadrants. So, what if he was trying to get down here into quadrant 4? Well, the logical thing to do would be to drop into the negative angles and just say, okay, I'm in quadrant 4. But what if you wanted to try to go all the way around the unit circle through 2 and 3 and into 4? You see him? Is he going to make it? No, he didn't make it. Why? Because it's lava. You can't walk through lava, right? I mean, here I go. I'm going to start. See? Stay out of the lava. I know it's not taught in school anymore like it used to be, that lava is detrimental to your health, but stay out of the lava. Let's talk about inverse cosine, okay? It's a similar discussion, but it is a little bit different. We've got positive ratios for cosine in quadrant 1. So once again, quadrant 1 is a real easy place to take your angles from, or the answers to inverse cosine problems where we're putting positive ratios in. The problem is with the negatives. We can't duplicate what we just did for inverse sine, mainly because what? Well, because not only is cosine positive in quadrant 1, remember cosine is related to x, and so we are still positive in quadrant 4. This requires us to eliminate that as a possible region. It just doesn't work. Doesn't make sense. Okay, so that means where are the negatives going to come from? Or at least that's the question that we need to ask. Here's our positive ratios, similar to the cosine problem, right? Coming out of quadrant 1, you can see that if I tried to use that negative quarter rotation, I would just be duplicating positive ratios. That doesn't help us at all. But what if I went forward instead of backwards? What if I went forward? You can see that the next quadrant, the next 90 degrees, the next pi over 2 radians, is that little region right there. And sure enough, that covers all of the negative ratios from 0 to negative 1. And so we're just going to take our negative angles for cosine, our negative ratios are going to generate angles from quadrant 2. Now, they're not going to be negative angles. They're going to be positive angles, because if I do this rotation right here, we're starting at 0, and we're stopping not at any kind of a negative value, but at 180 degrees, or 0 to pi radians. So that's the range for cosine which we're going to be getting our answers for, or at least for inverse cosine, that we're going to be drawing our answers from for those inverse cosine problems. We could also get negative ratios from quadrant 3, because cosine is negative in quadrant 3, but we can't go there, remember? Why? Because there's lava down there. Actually, because we'd just be reproducing negative answers that we already have. We only need all the positives once and all the negatives once, and we have it covered at that point in time. Okay? And that's it. I mean, those are the regions that you have to understand. Those are the ranges for the inverse trig functions. That's how you decide where to get your answers from. We're gonna call them lava zones for obvious reasons, because we've been talking about lava. This is not something you probably find in your standard high school or college trigonometry book, any discussions of lava of any kind, but I think it's a great reinforcement on why you don't want to go there, because lava is not healthy. It's not healthy to stroll through lava. For example, you know, our little woodcutter dude here is like, hey, how you doing? I'm going to try to get to a quadrant where inverse cosine is going to give me some angles that are coming from negative ratios, and okay, I'm over here, but no, that's not good enough for me. I want to keep cruising down into quadrant 3, and I don't care if there's lava down there. Big deal, right? Well, it was a big deal. You shouldn't have gone there, bud. Look, this is what's left after a stroll through lava. Bad idea. Stay between quadrants 1 and 2. Don't go past that, and you'll be fine. If you just take your answers from the 2 quadrants that you're allowed to take your answers from, these problems will be pretty easy for you. Tangent. How do you define tangent? And what about inverse cosecant, inverse secant, inverse cotangent? What about the remaining 4 inverse trig functions? The cosecant and secant are probably the ones that are the easiest to discuss, because the inverse cosecant is just 1 over inverse sine, isn't it? Well, I don't know if that's necessarily true, but we do know they're both based on y, and because of that, they're going to share the exact same regions, quadrants 4 and 1, where secant, which, you know, the inverse secant is going to be still connected to the x variable, and so it's going to take its lead from cosine, and it's going to have the same region as cosine. Tangent and cotangent are tricky for this reason. They're both positive in quadrant 1, so everybody's positive in quadrant 1. We know that's the case. But they're both negative in both quadrants 2 and 4. So you kind of can take your pick which one makes sense. These are the only ones that I think you're going to have to worry about keeping this straight at all, just because you could go either way and get an answer that actually makes sense. I'm not sure, 100% sure why these decisions were made a couple hundred years ago. I haven't done the research and looked up the historical reasoning, but I believe they split them up just to keep some symmetry to the inverse regions. So instead of having 4 inverse functions coming from one from 2 quadrants and the other 2 from the other 2 quadrants, then we had 3 and 3, and so because tangent could be considered, not inverse tangent, but tangent itself can be considered sine over cosine, and the top of it would kind of be considered the power part of that fraction, although that really doesn't necessarily mean anything. Sine is bigger in some places and cosine is bigger in some places, but if you think of the top as kind of the power part, you're going to know that tangent, inverse tangent, is going to go in the same region as inverse sine. Meanwhile, the cotangent was cosine over sine, and because the cosine's in the top, we're going to have the same region as the inverse cosine. That is not the reason that these decisions were made, or at least if they were, that would be bizarre. That's just kind of a way I have of kind of thinking about it, and hopefully that helps you keep them straight too. But this is our final kind of results for the lava zones. The inverse sine, inverse cosecant, and inverse tangent functions all have their ranges bounded from negative pi over 2 to pi over 2. The inverse cosine, inverse secant, and inverse cotangent functions all have their regions bounded from 0 to pi, or 0 degrees to 180 degrees. And if you can get these down, the inverse problems become actually pretty simple problems. And I think now that we finally have all of this agreed upon, at least to some extent, it's probably time to look at how we would apply these to some problems. Oh, by the way, one last thing here. We're not gonna actually. There's probably two more things I want to discuss, but then we'll do some examples. We're not going to get into the graphs very much. I think that's something we talk more about in math analysis. But if we were going to, here's something that we would be discussing. We just said that we're only going to take the inverse sine answers from negative pi over 2 to pi over 2. And so remember how this wasn't a function, it didn't pass the vertical line test? If we only start at pi over 2 at the top, and we take everything away, all the way, from negative pi over 2 down, you can see that suddenly our once snaking function up and down becomes a much more boring function, but one that now passes the vertical line test. The same exact argument could be made for the cosine function. I'm going to take away everything down to pi, and everything up to 0 goes away. And it looks like, by the way, there's a little typo there. That should be positive pi. Once again, the inverse cosine function now passes the vertical line test. And these are what the inverse functions look like. If you look them up in a textbook, look at these vertical lines I'm drawing. See how we don't have any more problems? These are the graphs you would see. Very different than a lot of the graphs you've seen almost throughout any other type of function that you've ever graphed through Algebra 2 and into this class, because they're extremely bounded. I mean, both in their domain and in their range. So it's a kind of a new type of function. And like I said, we'll discuss it in math analysis more. The other thing I wanted to talk about is just the fact that there are, depending on your textbook, other ways of naming these functions. We've always used the inverse sine concept, where you have the little -1 indicating the inverse function. But there are a lot of textbooks, a great number of textbooks that don't do it this way. Instead, they use the idea arc. Another way of expressing the inverse trig function is by calling them the arc whatever function we're dealing with. So for example, let's say we were doing sine, it would be the arc sine of x. And what this means is the arc whose, in this case, sine, remember that's the ratio, is x. The arc whose sine is x. Now, since the unit circle radius is 1, the arc whose, and it could be any of the functions, but right now if we're just going with sine to make it make sense, the arc whose sine is x and the angle whose sine is x have exactly the same meaning, because with a radius of 1, the arc length is going to be identical to your angle rotation, your radian rotation. And so they really have the same meaning. But to the point, a lot of books use this notation instead of the inverse notation. And so the inverse sine and the arc sine, these guys right here, they have exactly the same meaning. Okay, exactly the same meaning. Inverse cosine, arc cosine, exactly the same meaning. So if you ever are like taking a ACT or a SAT and suddenly you see this arc notation, don't freak out. All it means is inverse. arc cosine is the same as inverse cosine. Okay, but we're gonna keep using the inverse notation. And here's those examples I told you we were going to get to. What is the inverse sine of 1? Well, we know that the sine function has a ratio of 1 at pi over 2 angles, any pi over 2 reference angles. But remember, we're only going these two quadrants, quadrants 4 and quadrant 1, from negative pi over 2, where the sine would have a ratio of -1, up to pi over 2, where the y value is +1. And so since this is +1, that's our answer. Our answer is just pi over 2. Our answer has to come from between negative pi over 2 and pi over 2 for any inverse sine, inverse cosecant, or inverse tangent answers. What about 3 pi over 2? Well, there's the sine of 3 pi over 2 right there, and that looks like pi over 3 reference angles. Anything that's a positive ratio is going to come from quadrant 1. End of story. You're done. Don't make it more complex than it needs to be. Okay, that's just any positive ratio is always going to be located in quadrant 1, no matter which inverse function you're using. The ones you really have to think about your lava zones on are the inverse functions of negative ratios. And here's our first negative ratio right there. Now, we know that sine has a ratio of 1/2 at pi over 6 reference angles. But if I said the answer was pi over 6 and I looked at that in reverse, the sine of pi over 6 would be +1/2, not -1/2. So what we're going to do is we're going to drop down into quadrant 4, negative pi over 6, and that's now going to be in a quadrant that gives us negative ratio. So that's our answer, negative pi over 6. Okay, so for inverse sine and inverse cosecant and inverse tangent, positives are going to be positive angles up to pi over 2. Negative ratios are going to create negative angles down to negative pi over 2. That's really about it. Whatever you do, don't try to do this. Don't try to be like, hey, I know I need to get to quadrant 4, but I'm going to go all the way around here to like 11 pi over 6. It's true that the sine of 11 pi over 6 is -1/2, but 11 pi over 6 is way past the barrier of pi over 2. It was not the right answer, and plus you just went through 2 full quadrants of lava, so you've got much bigger issues than just getting the wrong answer there. By the way, the inverse sine of 0 is 0, so we'll end on that nice easy one for this first little set of examples. All right, next set of examples. Inverse cosine of 0. The inverse cosine of 0. Here's cosine on our table here, and here's the ratio of 0, and it looks like it's going to come from pi over 2 reference angles. Inverse cosine, remember, has different boundaries. It goes from 0 to pi for the answers, or 0 to 180 degrees. I'm mostly going with radians because that's what you're going to see more often moving forward with upper level mathematics. But the key here is that the only positive place where you're going to get an answer of 0 as far as a pi over 2 reference angle goes is at pi over 2. And so that's your answer, pi over 2. Okay, pretty much you can get that right off of your table of values. Now what about the next one, the cosine of √2 over 2? So let's see here. Here's √2 over 2. That's going to occur at pi over 4 reference angles. And once again, I implore you to consider, if it's a positive ratio, like √2 over 2 is certainly positive, your answer is always going to come from quadrant 1. So your answer is just pi over 4. The answer here is just pi over 4. Okay? Don't make it harder than it is. The ones where you have to stop and consider are always going to be the negative ratios. Cosine gives us a ratio of 1/2 at pi over 3 reference angles, but the answer can't be pi over 3, because pi over 3, the cosine of pi over 3 would give us a ratio of positive 1/2. Cosine is positive in quadrant 1. So we have to go into the negative quadrant, which is an angle of 2 pi over 3, and that gives us our answer. Now, this freaks some people out. And the reason is because we just did some sine examples, and when the ratios were negative, the angles are negative, and there's going to be some folks that are going to be like, wait, this can't be right. This was a negative ratio, but this is not a negative angle. This can't be right. But this is where you have to go back a couple months to when we first started discussing the unit circle and the whole idea of exact values and ratios. Whether or not a ratio is positive or negative has nothing to do with whether an angle is positive or negative. The only thing that matters is what quadrant you end up in. I could do a positive rotation, a positive angle that puts me in a quadrant where cosine is negative. I could do a negative angle rotation that puts me in a quadrant where the cosine ratio is positive. It doesn't matter, okay? If you have a positive cosine ratio, you take your answer from 0 to pi over 2. If it's a negative cosine ratio, the inverse cosine is going to have an answer between pi over 2 and pi, and 2 pi over 3 is certainly in there. What about tangent of 1? Well, tangent's a whole different ballgame, isn't it? Tangent is defined, once again, from negative pi over 2 to pi. It's the same as sine. And tangent is equal to 1 at 45 or pi over 4 angles, 45 degrees or pi over 4 reference angles. And because it's positive, quadrant 1, end of story. Pi over 4, we're done. Positive ratios, don't make them harder than they are. Tangent of negative pi over 3, so this one has a negative ratio, so it's going to be a little bit more interesting. It's a pi over 3 reference angle. And so we're going to have to drop down into quadrant 4 at a negative pi over 3 for an answer. Number 10 starts to get into these composite functions or composite expressions, which I know look a little creepy, but just do them in 2 steps and you'll be absolutely fine. Always do the inside first. Sine of 5 pi over 4, guys, is just like the problems we've been doing all semester long, where we find the exact value of pi over 4. Sine is the function. Pi over 4 is the reference angle. So I know that root 2 over 2 is going to be at least part of the answer. The question is it positive or negative? And it has nothing to do with, is 5 pi over 4 positive or negative? It has to do with what quadrant is 5 pi over 4 in. Well, pi is 4 pi over 4. This is in quadrant 3. Y is negative in quadrant 3, so the answer is negative. Okay. Now we start discussing the lava zones, because we want to know where sine is equal to what angle gives sine a ratio of negative root 2 over 2. And I'm going to erase this so we can kind of start fresh. And sine has ratios of root 2 over 2 at pi over 4 reference angles, but because it's negative, we're going to drop down into quadrant 4 at negative pi over 4, and that is your answer, negative pi over 4. That's it. We used the lava zone, we're done. Number 11, we used the lava zone right away. Where is tangent equal to a ratio of negative 1? Well, we know that tangent is equal to 1 at pi over 4 reference angles. And so it's going to be another pi over 4 situation, except this time it's just the interior part of the problem. We still have to figure out what the final answer is going to be. Also, this is a negative pi over 4 because the tangent ratio was negative 1, which meant we had to drop down into quadrant 4. What is the cosine of pi over 4? Well, the cosine of pi over 4 is root 2 over 2. And so the only question remaining is, what is cosine in quadrant 4? Well, cosine relates to the x variable, which is positive in quadrant 4. So positive root 2 over 2 it is. The last example like these, what is the inverse sine of 1/2? Well, there's sine. Here's 1/2. Looks like it's a pi over 6 reference angle, and it's a positive 1/2, so that's all there is to it. It's pi over 6, done. Don't make it more complex than it is. Positive ratios always are going to have angles coming out of quadrant 1. What is the secant of pi over 6? Well, let's see here. Secant pi over 6 is 2 root 3 over 3. And you don't even have to consider what quadrant it's in. It's pi over 6 is in quadrant 1, where everything is positive. That's your answer. 2 root 3 over 3. Always start from the inside out on those problems. Now, 13 looks like one of the problems that we just did, but then when we go to start asking ourselves where is tangent equal to a ratio of 1/2, we're like, it's not. I don't see it ever having a value of 1/2. Some students would stop right now and figure this is a great place to just say that it can't be done and move on to the next problem. But of course, we're not just like those students. We're like the ones who are going to ask ourselves, well, is tangent ever equal to 1/2? And we remember a picture of tangent from graphing it that looks kind of like that. And then we remembered the range of tangent is all real numbers. So of course, somewhere, tangent's going to have a value of 1/2. We just don't know what x value that's happening at. We just are not exactly sure where that's going to happen. So this is a different kind of problem. This is a kind of problem where we don't have a value that comes off of our table. And so our table over here becomes a little bit worthless, I guess. Bye-bye table. So what are we going to do instead? We're going to do another skill we've developed over the semester. We are going to build a picture. Okay? Now, notice that that ratio that our inverse tangent is operating on is positive. And it doesn't matter if it would be inverse tangent or inverse anything else. If it's a positive ratio, we're going to be in quadrant 1. Also, recall from your definitions of the trig functions that the tangent function is the opposite over the adjacent. And so we're going to have a 1 and a 2 for our legs. 1 squared plus 2 squared is 5, so our hypotenuse is going to be root 5. And how the heck does this little picture help us answer this question? Well, here's the idea, guys. Going back to earlier in our discussion today, the inverse tangent of a ratio is going to generate an angle. Now, what angle it is, unless we used our calculator to get an approximation, we don't know. But the truth is it doesn't matter. Whatever angle this is, let's just call it angle theta, okay? Whatever angle this is, we just drew a picture of it. Okay? And all that we're asking here is what is the sine of that angle? What ratio of that angle is the opposite over the hypotenuse? Well, now that I have a picture of that angle, I don't care what the specific angle is. I can look at it and I can determine that the ratio of the opposite over the hypotenuse is 1 over root 5, which we would probably want to rationalize to root 5 over 5 for our final answer. Similar problem on number 14. The cosine of, remember, inverse sine of negative 1/3 is just a big old angle, but I don't know what angle it is. Sine on the nice special right triangle rotations is never equal to a ratio of 1/3. So we're going to have to build ourselves a little picture here. So here's our picture. This time the sine ratio is negative. And so if you know your lava zones, we have lava here. We have lava here. You can only build your triangles in quadrant 1 or 4 because it's a negative 1/3, right? Negative 1/3. We're for sure building this one in 4. So the lava zones tell you on these types of questions where to build your triangles. Let's use the Pythagorean theorem. 9, 3 squared is 9, subtract 1, negative 1 squared is 1, is root 8. And root 8 would reduce to root 4 times root 2 or 2 root 2. Do we need that? I think we do. Because remember, the ultimate goal here is to determine the cosine ratio from this angle. And we just built a picture of this angle. Perhaps, the full rotation of this angle was, all the way around like this, but we don't really care about that. The reference angle is what we're building the triangle with, and the reference angle is going to match up to the angle in question. The cosine is the adjacent over the hypotenuse. The adjacent was 2 root 2. The hypotenuse was 3. We're done. 2 root 2 over 3 is our answer. Similar question. I'll do this one a little bit more quickly. The reason for this one is just to show you that lava zones aren't always built for negative ratios in quadrant 4, because inverse cosine is not even defined in quadrant 4. Inverse cosine has lava down here. We can't go down there without dire consequences. So what we're going to do for our negative cosine ratio is build it in quadrant 2. That's where the cosine angles generate negative ratios. So this is kind of like our theta rotation, although this is our reference angle that we're using. Cosine is adjacent. Make sure that's negative. If you lose your negative signs when you label your axes, you're gonna get some wrong ratios. Over hypotenuse, that's cosine. And then let's see here. This is just like the one we just did, right? 9 minus 1, so it's root 8 or 2 root 2. And this time I'm looking for the tangent. The tangent is the opposite over the adjacent. And so the tangent is going to be 2 root 2 over negative 1 or negative 2 root 2. One last question and then we're done, I promise. Okay? One last question. What we have here is the sine of one angle plus another angle. I mean, when you first examine this expression, it just looks ugly, and a lot of people just have no idea what to do with this. It just looks like a bunch of gibberty something. Jibber jabber. How about that? Okay? If we examine it a little more closely, the inverse cosine of a ratio is just one angle. The inverse sine of this ratio is also an angle. They're probably not the same angles. In fact, I know they're not the same angles because one of them has a hypotenuse of 2 and one of them has a hypotenuse of 5. And so that's why we give them different names. Because of the sum and difference formulas we've been using, we used a lot of alphas and betas. That's why I named one of my angles alpha and one of my angles beta. You could name them A and D, X and Y, Joe and Fred. It's really up to you what you name them. I'm just going to go with alpha and beta. So really I've got the sine of alpha plus the sine of beta, and I have a formula for that. Isn't it sine alpha cosine beta plus cosine alpha sine beta? Isn't that really what we're looking at here? So all we need to do is come up with 4 ratios, plug them in to this angle sum formula, sine of the sum of angles formula, and then simplify it, and then we're done. The problem is we don't know all the ratios. We actually do know a couple of them. The cosine of alpha is 1/2. The sine of beta is 3/5. But I don't know the sine of alpha or the cosine of beta. And so just like on the last couple problems, what we're going to do is draw some triangles, except we're going to have to build 2 triangles this time. An alpha triangle and the beta triangle. The alpha triangle can only exist in quadrants 1 and 2, because for inverse cosine, there's lava down here. The beta triangle can only exist in quadrants 1 and 4, because lava is in quadrants 2 and 3. This is actually a pretty simplistic problem just because both ratios are positive. That means they both have to come out of quadrant 1. What's our 1/2? triangle for the cosine. Isn't that adjacent over hypotenuse? And 2 squared minus 1 squared would be 4 minus 1, which is 3, so square root of 3. And then for the beta triangle, the opposite over the hypotenuse is 3/5, and this is one of our very best friends, the 3, 4, 5 primitive right triangle. But now we know what our missing ratios are. The sine of alpha, if we look up at the alpha triangle here, right? If we look up at this dude right here, the opposite over the hypotenuse is root 3 over 2. And the cosine of the beta triangle, cosine, the adjacent over the hypotenuse would be 4 over 5. And let's go ahead and plug those in. So root sine of alpha, root 3 over 2. And cosine of beta, 4 over 5. Now it's just a little bit of algebraic simplification, and I think we're done. 4 root 3 plus 3 over a common denominator of 10, and rock and roll. Our last example is finally over. So I know this is a pretty long video, but I do hope that the explanation was a little bit deeper and helps you understand this stuff at a slightly deeper level, which will help you remember it a little bit longer. Here's some problems here on workbook page 412 that'll help you practice some of these ideas. Look, if you can't remember how to do some of the problems, you might look back at the video. Probably don't have to look at the whole thing, but maybe fast forward to the examples part. And then for some more fun, you can do problems 1 through 12 and 25 through 52 out of the textbook, page 228. But be very, very careful. Why? Because you don't want to end up in the lava. And even if you don't end up in lava, if you're going into the lava zones, I may import some of my own lava and give you a little taste of a lava shower. Actually, I wouldn't do that and wouldn't even know where to start. I don't think you can import lava, can you? Anyway, if you are real sneaky, here are the answers right here from page 12 of your workbook, so you can kind of check and see how you're doing. And then, of course, out of the textbook, here are the evens. So if you have a little pause button on your computer, you can check those out. Don't end up like this dude. Stay out of the lava zones. And I hope you are now understanding the inverse trig functions a little bit better, where their ranges are defined as and why they're defined that way. And we will see you in the future.